Hello, welcome. Now, we are done with magnetic field of a straight current carrying wire. So let's talk about force between parallel wires. So we are going to use this formula here, so let's remember this. When you have an infinite wire at a distance x, you will get this much magnetic field. Okay, so let's think about two wires. Force between parallel wires. Of course, we are going to assume that these wires are very long. Okay, these wires are very long, but their distance is short in comparison to their length. Okay, so let's say this wire carries I1, this wire carries I2, and there is some distance in between. The distance is D. The length of the wires are L, and L is much larger than D. Okay? So let me ask you, what is the magnetic field on top of this wire because of this wire? Yes?
Mu 0 I1 over 2 pi d.
Mu 0 I1 over 2 pi d. Because you are using this formula, right? You are saying that this wire, this red one, will create a circular magnetic field around it, right? And I already pointed it in. How did I find it? I put my thumb in the same direction as the current, and my four fingers would wrap around the magnetic field. Okay? Good. So, and the magnitude of that field, B1, let's call it B1, is mu 0 I1 over 2 pi d. Okay. So far, so good. Let's talk about the other wires. Let me just take this to the other side. How about the other wire? The other wire will also have a circular magnetic field around it.
Towards us, pointing out of the plane.
Pointing out of the plane. Very good. Because you again put your finger and wrap it around, and it comes out on the other end. And B2 is mu 0 I2 over 2 pi d. Everybody agrees? Yes, good. Now, let's figure out the force. Let's first figure out the direction of the force. So this wire will feel a force because of the magnetic field created by the other wire. And we are going to do L cross B to find the direction. L goes up, B goes in, it's towards left, right? So this is F, and F2 because of 1 is basically B1 times L times I2, right? So F21 is mu 0 I1 I2 L over 2 pi d. If you do the same thing for, this was F21, you will see that F12 is the same and opposite. F12 has the same magnitude but opposite direction with respect to F21. Okay? Yes. Okay, so they will be attracting each other with this force. Do you have any questions at this point? I think you did know this from high school, did you? So when the currents are in the same direction, they would attract each other. Then the force would be attractive. When the currents are opposite, like this, then they will repel each other. Okay? Is this how you spell repel? Or is there another L here?
Should be like this, right?
Attract.
Attract.
Yes. Okay? Yes.
Hocam, while finding the direction of magnetic field, which two vectors we are looking for, like referencing?
Very good question. So let's remind ourselves. So let's say this is I1, right? And I wanted to find the magnetic field to the right, right? Towards the right of this. So then the dl is pointing in this direction and r unit vector is pointing in this direction. dl cross r is pointing in. Thank you. So let me also put this one over here in case you want to see it. Any other questions? No? But you can also use this, just your thumb. That's also nice. So we use this actually to define Ampere. So let me talk about definition of Ampere.
Definition of Ampere's law, or just
No. Definition of 1 ampere. What is 1 ampere? 1 ampere is the current when force divided by length is equal to exactly 2 times 10 to the minus 7 Newton per meter. So you adjust everything else with respect to this, okay? So you have, for example, some definition for time, which is based on cesium atom. Is it? Because is it defined by speed of light? Because they keep changing it.
Yes, probably. I don't know.
It used to be defined by like I'm just making up a number, okay? 9 billion something, 576,000 and blah, 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 number of cesium atom decays or oscillations. That would give you 1 second. Let's say you get 1 second from there. You get 1 ampere from here. 1 ampere times 1 second is 1 coulomb. That's how you define coulomb. Okay? So that's why you need this 1 ampere definition for 1 ampere, and this is how you do it. Of course, given D is equal to 1 meters. Okay, like it's simply this. Okay, F over L must be mu 0 times I1 times I2 over 2 pi d, right? So since mu 0, we set mu 0 to exactly 4 pi times 10 to the minus 7, what you have to get from this, when this is 1 meter and these both of them are 1 ampere, then you have to get 2 times 10 to the minus 7 Newton per meter. Okay? That's basically how you define ampere. Yes.
How do you find mu 0 I over 2 pi x?
Very good question.
Because I was looking at my notebook and we didn't like derive it or something.
Yeah, it's right here. Do you see it? Right
It's
before
just
the
a
end.
formula.
Right before the end.
Uh-huh.
So do you have in your notebook the solution of magnetic field of a straight current carrying wire? Do you have that?
Yes.
At the end, we took a to infinity.
Ah, okay.
Okay?
Mm-hmm.
So when you take a to infinity, it's an infinite wire,
Mm-hmm.
and you get
So it becomes
an expression for magnetic field. But you're welcome. We will have a much simpler way of getting it. Okay? Yes. All right. So far, so good. You know how to define ampere now. All right. Let's talk about magnetic field of a circular loop. Let's say you have a circular loop like this, and there is some current running around. Let's say it's I, and the distance from the center is R. First of all, which way is the magnetic field? Out of the page. Do you agree? Out of the page. You can. This always works. Okay, you can just wrap around the current, and this will. Do you see how many different uses this has? Just before we put this one to current, and we got this one as magnetic field. Now we are putting this one to current. We are getting magnetic field from this. So it always works. Or if you want to go back, you can basically think of it this way. What is the magnetic field from here? It's outwards, right? What is the magnetic field from this? Also outwards. Do you see? So it just goes out. Good. So magnetic field is pointing out. So to find this magnetic field, we need to remember our formula, Biot-Savart, right? Mu 0 I over 4 pi dl cross r unit vector over r squared. In this part, this is Biot-Savart in general. In our case, it's mu 0 I over 4 pi. And what is dl?
dl is r d theta.
Yes, or just dl, right? Let's just go with dl. And cross r is just dl because r is a unit vector, and there's 90 degrees everywhere. No matter where you take dl, you always have 90 degrees with where it points, right? Let me just, this vector, r unit vector, is always perpendicular to dl. All right, over r squared, and this small r squared never changes. It keeps being r squared, right? Let's integrate. Let's go from 0 to 2 pi r, the whole length of the wire, and we simply get mu 0 I over 4 pi r squared times 2 pi r. Pi's go away, one of r's is cancelled, so we get this. Let me write it down here. B is mu 0 I over 2r. Notice that when you have a circular loop, you lose pi. This is one of those rare cases where you do have a circle facing at you and you actually don't have pi in the formula. Don't forget that. Yes, exactly. So, but remember, this one has a pi in it. They look very similar. Do you see? Infinite wire magnetic field created at a distance r is mu 0 I over 2 pi r. This one is mu 0 I over just 2r. Good. Okay. Let's look at this example. Let's try finding out what is the magnetic field at a distance x for this object. This wire also carries current in this direction, and okay, there's a drawing problem here. Should I draw it again, or should I just say that this part is closer to us? Do you understand it now? That part is closer to us, so it's rotating like this, not like this, because you can see it either way. Okay, let me change the picture a little bit.
I still don't understand what the problem is.
Now you know which way it turns. Do you see what I mean? I just put this tube there to show you that this portion is far away from us. Okay? Because you could have seen it the other way around. Okay? Okay, good. Yes, I'm sorry. So this time I was careful, but I'm not always careful about this. So I want to find the magnetic field at this point over here. So what should I do?
Find the magnetic field due to a small part of
So let's find. So our dl is pointing out of the page here, right? Actually, let me show it pointing out of the page, because the current coming out of there. And if I plot a distance over here, that's dl, and this is your r, right? So this is your r unit vector, and dl points outwards. Are you following? dl cross r is pointing
in the y and x plane.
This way, right? It's pointing this way.
It has y and x components.
Do you agree with this? Yes. So it has to be perpendicular to both dl and r unit vector, and that's perpendicular to them. Good. So you can imagine that if you think about this portion of dl, which is the symmetric portion of it, then that one would have a magnetic field pointing down. The same amount. Okay? So as a result, we don't care about y components. We do care about x components only. Okay? y components cancel each other out. I used very confusing colors here, so let me just make this one green and this one red. Okay, there you go. Efe, how are you today?
Thank you, William, for asking.
So y components are cancelled, you only have x components. No problem there, right? No problem.
I didn't understand how you found DB's.
Sure. DL comes out of the page. Do you agree with that? Over here, because current is coming out of the page. R is pointing to this point. Make DL cross R. So DL comes out like this. R goes that way. So if you do this, your thumb is pointing this way. Do it.
Isn't it like out of the page or something?
No, you have to do it to see it. DL goes out.
Uh-huh.
R goes this way.
Okay.
Yes? Or let me just not do this. So DL goes out,
Mm-hmm.
R goes
Down.
this way, right?
Mm-hmm.
Then,
Okay.
okay? Same for the other one. Good. So I only care about the x component. What is the x component? How can I find the x component? I can just simply say, let me call this one theta. Then this one is also theta. So I'm interested in only sine of theta, right? So I'm interested in dB times sine theta, which means I'm interested in mu 0 I over 4 pi times r squared plus x squared, right? Times dl. dl is by itself, but there is a sine theta and it comes from component of the magnetic field, right? Otherwise, you can still integrate from 0 to 2 pi r. Okay, what is sine theta?
So this is r over, the square root of r squared plus x squared.
Sine theta is r over square root of x squared plus r squared. Very good.
And it remains constant.
Yes, and it remains constant. It's again just simple dl integral. So we have mu 0 times I times 2 pi times r over 4 pi r squared plus x squared to the power of 3 over 2. Right? So, what is the result? Magnetic field is mu 0 r squared over 2 x squared plus r squared to the power of 3 over 2.
I, and also I.
And there is also I, which I miss on my notes. Thank you very much. All right. So for this one to be equivalent to what we have found here, what x has to be?
X has to be 0.
X has to be 0. Right? When x is 0, do you see that this formula and this formula are the same when x is 0? Yes? Good. Okay. So, do you have any questions? Before the exam, we will solve all kinds of these weird questions where we will have like this kind of wires coming in and going on. You will get used to this stuff more and more, but let's leave it to
Next week.
next week. Let me talk about turns. When your wire has actually turns, for example, or loops, number of loops and turns. So for example, this one has n equals to 1 turn, and its magnetic field, let's say, is mu 0 I over 2r, right? But this other one has 2 turns, number of turns is 2, then the magnetic field is n times b, which is 2 times mu 0 I over 2r. You understand this? You either think about it as a wire having turns, or you can also think about it as doubling the current. Like there are, two I's here. So not I, but two I's, because they are rotating in the same direction. Okay? Good. Now we are ready to study this law that would make things simpler in certain cases, and it's Ampere's law. Okay, it's very similar to Gauss's law, but here what we have is a line integral. So we have B dot dl equals to mu 0 times I enclosed. And this is a 1D integral over a closed loop. Okay? In Gauss's case, it was an integral over a closed surface. This is an integral over a closed loop. So let's use it right away. Let's just put nice brackets on top of it. Yeah. Okay, for example, I take, okay, can you always use it? No, this one still needs, you need symmetry. Just like in the Gauss's law, it's, one can say that it's even more restricted. Okay, like we will only use it for cylindrical coordinates when you have wires going to infinity. When you have a wire not going to infinity, you cannot use it. Okay. For example, you cannot use it for this wire. You cannot just take an Ampere loop and say that this is magnetic field. That doesn't work. It doesn't work like that. You need this symmetry. So it's a bit harder to understand the reasons around it, but for now, please take it for granted that we will work with infinite wires here. Okay. Let's apply it in the simplest case when you have a circle around this wire. There is a current coming out, right? And you have a path here, and that path, the direction of that path follows the, I mean, you are the one who drew this path, okay? But the direction is determined by the current. Whether it's going out, then the direction is in this direction. If it's going in, then it's in this direction. Okay? Again, you use your right hand to see which way you have to rotate. But otherwise, this is the situation, and you already know that there will be a magnetic field, and from the symmetry you know that it will be like this, the same everywhere around this circle. So what Ampere's law tells you is that B dot dl integral, which in this case will be just B times dl, because they are always aligned. Do you see? B and dl are always pointing in the same direction. And this loop integral should give you mu 0 times I, because that's the amount of current that this loop is enclosing. And loop integral of dl is just 2 pi r. So B times 2 pi r is equal to mu 0 I. I don't know if you remember the integrals we had to take to arrive at this result. Do you remember the integrals? These are the integrals. But here we arrive at it very easily. And one more time, we remember that for an infinite loop, the magnetic field around it is mu 0 I over 2 pi r. And this time we found it using Ampere's law. Please let me know if you have any questions. Do you have any questions? Okay. So what if you had a current, but you had a loop like this somehow? Would it work? And the answer is yes, it would. So you see, dl, it would work, but it would not give you any good information. It's just if I ask you find this integral around this path, okay? But notice that over here, for example, magnetic field would point in this direction. Over here, it would point in this direction. Over here, it would point this way. Over here, this way. Over here, this way. It's not necessarily aligned with dl. Do you see? This is dl. But if you integrate all those different b dot dl's, then you will get what? Mu 0 I. Okay? Let's say this is I1 and this is I2 going in. What do you get? Mu 0 I1 minus I2. Do you see what I mean? Okay. Good. Very, very good. So let's say I have a current over here and I have a loop over here. What is B dot dl here?
It should be 0.
0, right? Why? Because it's not enclosing the current.
And it doesn't mean that B is 0 on the loop.
It doesn't mean that B is 0, right? It just means that B dot dl is 0, integral. Very good. So, as I mentioned, the examples where you can use Ampere's law are not that too many. I said only cylindrical coordinates, but I was lying to you. There are also other situations. We will come to that one as well. But it's combination of cylindrical coordinates. When you have infinitely many wires set around so that you make a surface. Okay?
Can we use a loop that is a square? For some cases, it might work, right?
It would work with a square only if No. No, it would, the most, I was talking about this one. Like if you have a sheet which is very, very long in one direction, then you can still use Ampere's law, but not otherwise.
Can I ask something?
Sure.
Suppose we have a cylindrical object.
Yes.
There's an what should I say? Insulating object.
Yes,
charged
I'm going
uniformly, and it is rotating with angular, speed.
Yes,
omega.
yes.
And how am I supposed to use Ampere's law to find the magnetic field at some point if there is symmetry?
Okay, so this is a good midterm question, right? So you have like a cylinder, it has sigma, and it's rotating like with omega.
Not sigma, rho. It is insulating.
It's insulating, okay.
It is filled.
Yes. Yes, you can use some sort of Ampere's law here, I
Can't
guess.
I use square root here to find it on the rotation axis?
No, this one would still not work. It would work only if it's a cylindrical shell. Okay, that's better. Then it looks like a solenoid. Then you can do some stuff here. But otherwise, it's complicated. Let me give you a very, very simple, a much simpler example. And we will come back to this when we solve questions.
With
Okay.
rho or sigma? Will it be
With
almost-
sigma.
Okay.
This one is, let me think. Okay. Here it is. Very. This is just a wire, and it's a cylindrical wire, and it is carrying a current that is uniformly distributed. Does it make sense? What is the magnetic field inside this wire at a distance r and outside this wire? I hope it makes sense. So let me just move it in and duplicate, and I'm also wondering what is it on the outside. So let's start with inside.
Is this a hollow cylinder?
It's not. It's a filled cylinder cable, and current is uniformly distributed throughout the cable. So it's proportional to its area. You see what I mean? Okay, so what is the magnetic field inside? Of course, the direction of magnetic field will be this way, right? The magnetic field inside times 2 pi r must be mu 0 I enclosed, right? What is I enclosed? How much current is enclosed by this green part?
Small r over capital R times R.
Is uniformly
Uniformly distributed. So I enclosed is I times,
Yeah, small r over capital R. It wasn't that.
how about small r squared over capital R squared? It's proportional to the area. Yes?
Pi r squared.
Yes, pi r squared over pi r squared, and pi's go away. Yes? So B inside of this wire is going to be mu 0 I r over 2 pi r squared. Can you please check? What do they say in the plane? Cabin crew cross check. Yes? Good. Outside, let's talk about outside. Let me just change this style to red. And let's talk about outside. B r greater than big R times 2 pi small r equals mu 0 I enclosed. What is I enclosed in this case? Just I. Exactly. So it's simply I. Since this one is simply I, then for outside I have mu 0 I over 2 pi r. That's it. Okay? Good. A nice application of Ampere's law.
Then is this the same as this surface's magnetic field? Just the big R, but the same formula. In the surface, like R equals big R.
Yes, so let me show you. So if you plot it with respect to R, let's say this is big R, this is big R, so it will come linearly until here, then it will decay like this. Okay, at the midpoint they will have the same values because at R equals to big R, this formula is equal to this formula. Do you have any questions? So let's talk about solenoid. What is a solenoid? It's simply something that, okay, let me not forget to do this. This is just a cylinder to show you the geometry of the system. Otherwise, it has no meaning.
It could be just wires without any material.
Yes, yes, yes. I'm just using this to show you which way it. Okay, something weird happened here. Yes. Okay. So how many turns do we have here? Let's say n turns. Okay. And over here, let's say you have a current going in, which means that that current will come out of these points all over here, right? Coming out, and it will be going in over here. I'm talking about the current. Okay. So the question is, what is the magnetic field inside and outside of the solenoid? It's not only a question, it's also a description of the solenoid, so in general. In general, our solenoids, for our solenoids, what we think is that R is much smaller than L. And in general, we think that it's very tightly wrapped. So basically, what you have is a series of currents going out, and very close by a series of currents going in. Okay? Yes, tell me.
How could we determine the directions, like red and green ones?
You mean the direction of the magnetic field?
Yes, we do all that.
Let me tell you. So, for example, let's think about the direction of the magnetic field inside. Okay, what these currents want to do? Which way they want to create the magnetic field? Towards right, right? Like only these ones are trying to create the magnetic field towards right over here. Okay, and these ones are also supporting that. So inside there will be some magnetic field because these ones are going in, these ones are going in, so the bottom ones. So the magnetic field rotates like this. For this one, it rotates like this. So over here, it's like two things bringing it together. But outside, it's like this versus like this. And outside, over here, it's like this versus this.
I mean, outside the magnitudes differ.
Yes,
You
but
should draw perhaps arrows smaller than
yes, I should perhaps. But the thing is that if you have enough number of these, and if they are very, very close, what happens is that it's like parallel plates and electric fields. If you remember, the electric field created by this one was cancelled from all over here. That's pretty much what happens with magnetic field in this case. So what happens is that we will assume that outside the magnetic field becomes 0. Okay, assuming that L is long, lots of current going in, out, and stuff like that. But inside, it's non-zero. Okay, that's what we are going to assume.
In the notes, they are reverse,
Yes.
So is it important? That's why I was confused, like, because of the
Yes.
current also comes from the,
Are you confused by the fact that here it is this way, here it is this way?
No, the fact that, green, nasıl söyleyeyim bilmiyorum. Şu şey, yuvarlak yeşiller aşağıda, orada yukarıda.
Yes. You mean
Ama akım aynı yerden geliyor.
this magnetic field is created by these ones. But also this magnetic field is created by these ones and they cancel each other out.
Ama işte onlar notta hocam şurada. Yukarıda ve akım aynı yerden geliyor. Ben o yüzden kafam karıştı yani.
Yes, do you mean that these ones are closer so they will be stronger?
Yok, noktalar aşağıda demek istiyor.
Evet
herhalde
yani
notlarla.
içe doğru. Yukarıdaki yerde bunlar içe doğru.
In your notes.
Ben diğer notlara
Fatal error veriyorum şu anda.
Çizimler sıkıntılı hocam. Çok şey yapmamışlar. Siz 3 boyutlu çizmişsiniz. Burada 3 boyutlu çizmemişler. Böyle karışık karışık. Büyük ihtimalle farklı çizmek istediler.
Ha, bunlar sizin notunuz. Bunları siz yazdınız. Öğrenci mi yazdı bunları?
Yok, ben yazdım.
Hata yapılmış geçen sene.
Let's have a
Şey, bu yuvarlak akım
Tell me.
çıkan şeyleri-
say it again. Say it again, please. Say it again.
Anlamadım şu. Şimdi baktığımızda akım içe doğru. Şu aşağıdaki
At the bottom it goes in.
şu yeşil yuvarlaktan bahsediyorum.
Yes.
Burada onlar yukarıda.
Yeah, don't worry about that one. Look at this one. I drew this now. I didn't look at this one.
Ben şey soruyorum hocam. Bunun hani bir farkı oluyor mu? Çünkü akım aynı yerden geliyor yani. Bu
No, if it is like this, then magnetic field inside is this way. If it is like this, then magnetic field is this way. That's the difference. Whether it's rotating like this or chirality. What is the chirality of this? Chirality.
Öğrenci kimyacılar dışında adam bilir mi ya? Bize onları gösteriyor.
Chirality. Let's have a break.